Hello class, I hope you are having a wonderful day. Today I would like to complete a practice problem with you involving the coefficient of kinetic friction. So I'm going to read the problem to you, I'm going to underline some important information, and then I will work through the problem. So let's go ahead and get started. A crate with a mass of 1,100 kilograms is being pulled along a greased track by a winch. The winch is exerting a force of 2,850 newtons in the horizontal direction along the tracks. The coefficient of kinetic friction between the crate and the tracks is 0.2. Now, on part A it says draw a free body diagram. Now before we draw a free body diagram, let's just go ahead and list some knowns and unknowns. So some important information that I underlined. We have a mass of the crate. So I'm going to say M sub crate is equal to 1,100 kilograms. The applied force of the winch, so I'll say F sub A for applied force, is 2,850 newtons. And the coefficient of kinetic friction between the crate and the greased tracks is 0.2. And coefficient of kinetic friction is identified by the Greek letter mu. And since it's the kinetic, I'm going to use a subscript of k. So what I have is mu sub k, and this is equal to 0.2. Now before we draw a free body diagram, let's just draw a very simple picture. So what we've got is a crate, and here's my floor, and the mass of the crate is 1,100 kilograms. There's a cable attached, and there's a winch, and the winch is mounted to something, okay? The applied force of the winch is, let's take a look at our knowns and unknowns here, 2,850 newtons, okay? Now, if we're going to draw a free body diagram, let's start out with the weight force of the crate, identified by F sub g. And we know the weight force due to gravity is equal to the mass of the object multiplied by the acceleration due to gravity. The mass is given to us. It is 1,100 kilograms. And the acceleration due to gravity is negative 9.8 meters per second squared. Okay, let's go ahead and take out our calculators. And we get a negative 10,780, and the units, we have a kilogram meter per second squared, so that's a newton. And the vector is negative. Our force vector is negative for weight because the vector is pointing in a negative y direction. So we have, here's our vector pointing in the negative y direction. So we do not need to apply the negative here since our vector arrowhead is pointing down. That is 10,780 newtons. Now, let's take a look at our normal force here. Our system is in equilibrium in the y direction. That means the normal force is equal in magnitude but opposite in direction to the weight force due to gravity. So, our normal force, identified by F sub n, 10,780 newtons, and our vector arrowhead is pointing up in a positive y direction. Now, we have an applied force of the winch right here, F sub A. The winch is applying a force of 2,850 newtons. And now we have a force of kinetic friction. So the force of friction is identified by F sub F. but I'm going to utilize my parentheses and use another subscript to help describe this force. This is the force of kinetic friction, so we definitely want to add that subscript of K there, okay? So this is our free body diagram right here. So this is part A, but let's go ahead and calculate the force of kinetic friction. So we know that the coefficient of kinetic friction is equal to the force of kinetic friction divided by the normal force applied to the object. So we have kinetic friction force in the numerator. In the denominator, we have the normal force applied to the object, okay? Now, this is our unknown. The force of kinetic friction is right here. This value is unknown. Now, we know the coefficient of kinetic friction because the problem gave that to us. And we know the normal force applied to the object because we calculated that. So what I'm going to do is isolate the force of kinetic friction by multiplying the normal force on both sides of the equal sign. On the right-hand side of the equal sign, normal force will cancel. So this is going to give me the kinetic friction force is equal to the product of the normal force applied to the object and the coefficient of kinetic friction. So the normal force, 10,780 newtons, multiplied by 0.2. The kinetic friction force is equal to 2,156 newtons. Okay? So let's go ahead and label that in our free body diagram. Now I'll just label it right up here. And that will satisfy part A for our problem. On part B, it says calculate the net force applied to the crate. Well, let's take a look at this. In the y direction, the system is in equilibrium. Okay, so we have net force in the y direction is 0, so it's in equilibrium. But in the x direction, we have a net force because we have more force pointing in the positive x direction. So for part B, we know that the net force applied to the object is going to be the sum of the forces, and specifically, we're looking for the net force in the x direction, or the sum of the forces in the x direction. So this is going to be equal to my applied force plus my kinetic friction force. Now my applied force, remember a force is a vector, so not only are we including the magnitude, but we are going to include direction. So my applied force is pointing in a positive x direction. So we're going to have a positive 2,850 newtons plus our kinetic friction force. Well, let's take a look at the vector. The vector is pointing in a negative x direction. So this vector will be negative 2,156 newtons. So the net force applied, I'm going to use the subscript of x again to describe the direction. So 2,850 minus 2,156, my net force is a positive 694 newtons. So this will answer part B. And part C asks us to calculate the acceleration of the crate. Well, what we're going to do is use Newton's second law of motion. And Newton's second law of motion tells us that the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. Well, we have calculated the net force. We're going to use this calculated value, 694 newtons. We're going to divide it by the object's mass. The problem told us the object's mass, the mass of the crate, is 1,100 kilograms. Let's take a look at the numerical value first, and then we will talk about the unit value. So 694 divided by 1,100 is equal to 0.63. Now let's take a look at the units. In my numerator, I have the unit of Newton, and we know that 1 Newton is a kilogram meter per second squared. And in my denominator, I have kilograms. And algebraically, we can write our denominator as kilograms over 1. And let's think about the old algebra rule that tells us whenever we divide fractions, it's like multiplying by the inverse of the denominator. So what I have is kilogram meters per second squared times the inverse of the denominator, which is going to be 1 over kilogram. As you can see, the units of kilograms are going to cancel out, leaving us with units of meters per second squared. So the acceleration of the crate is 0.63 meters per second squared. Okay, I hope me working through the problem has answered some questions for you. I hope this helps. If you have any questions, please let me know. You can call me or send me an email. I hope you have a wonderful day.